start with the first lecture, and I will talk about the MaxQuant basics. So I will introduce MaxQuant, and then I will also describe the implemented workflow there. I will cover one part, and then there is also MaxQuant Basics 2, where the session is then tomorrow, and this will then be presented by Jürgen. So probably you have all heard about MaxQuant. So it's a software for the analysis of shotgun proteomics data, but as we heard already, it will also be able to, or it's also already able to analyze DIA data and top-down. So the development of MaxQuant started in 2007, so that's already quite a long time. And so there's also continuous development, and so there's always an implementation of new features, and this makes the software quite mature and also efficient. And then also based on the number of citations, so this year we have already more than 6,600 citations. It shows that many people are using MaxQuant, and we are very happy about that. And also it seems like based on the previous years that there is a linear growth. So MaxQuant is freely available, so you don't need to pay for it, and it can be used by academics but also non-academics, so also companies can use it. So in Jürgen's lab there is not only the development of MaxQuant, so which does the identification and quantification of MS raw data and spectra, but also there is the implementation of Perseus, which does then the downstream analysis. So here, to give you an overview what each software does. So as I said, MaxQuant does analyze the raw mass spec data, which comes usually from high resolution, and then the peptides and proteins are identified with the integrated database search engine Andromeda. And then also it does the peptide and protein quantification. In MaxQuant there is also a viewer developed and integrated where you can see those mass spec data, so the MS1 features, and you can also visualize like the MS2 spectra, which are identified or unidentified. And if they are identified, you even can see like which peaks are matching, that you can go there directly if you're interested to see which peaks are matching, how is the quality, that you get a better idea. So more about the viewer we'll hear in the second tutorial tomorrow, and after this lecture I will also tell you in detail how the database search engine Andromeda works. So if you have done your MaxQuant analysis, you get a bunch of output files, so they are usually tab separated. And then depending on your interest, so there is a view on protein groups, but if you do PTM analysis, specifically phosphor analysis, then you also have a separate output just for the phosphosites. And so it really depends what you're interested in. And those files are tab separated, and then you can load them into Perseus. But Perseus does also accept any file as long as it's tab separated, so it does not necessarily need to be from MaxQuant. So as I mentioned already, Perseus does the downstream analysis. So there are many bioinformatics algorithms available in there which you can use. Then you can do data normalization. Then there are many statistical tools available. And then you can visualize your data to interpret it that better and make sense out of it. So for instance, you have volcano plot, Hawaii plot, rock plot, histograms, so you have a big choice. There are also several clustering algorithms available, and you also can visualize those by the heat map. And then you can integrate other data sets for like annotations to do. Yeah. Then also what I would recommend, so my colleagues published a review on computational methods for understanding mass spectrometry-based shotgun proteomics data, and so we already, I will explain you a lot about the workflow and what is done there, but if you want to dig deeper, this is a good read, and I can highly recommend that to read. And it's also not only just about MaxQuant, but it's also about other software tools. Then here is another important paper I can highly recommend. So a question to the audience: how many of you are using MaxQuant the first time? Okay, so I hope when we go to the tutorials, don't be afraid, because there are many parameters. And also, I think, as I can remember back, as I opened the first time MaxQuant, I thought, like, oh dear, I'm also not an expert, so how should I start it? But it's really good that there is only a handful of parameters you really only need to set. And the rest is only when you have specific questions. And so all those parameters are explained in detail in that protocol, so you can read that up. And so these are the handful of parameters which you need. And so if you set those, and then if you press start, then you can be quite sure that you have at the end reliable results. So let's go into detail into those parameters. So first of all, here you can set your experimental design. Why would you want to do that? That is because sometimes you have biological replicates or fractionations, and when you do quantification, you might want to combine those raw files because they are similar data to quantify them together. Then you can also specialize the type. And so this is also in terms of quantification when you want to do label-free quantification or MS1 or MS2 labeling. Then we will also learn later why the digestion enzyme parameter is important. So here that you also need to specify. Just a brief explanation. So when you do the sample preparation step, typically in shotgun, you chop your proteins up into peptides, and this you do by, for instance, trypsin, and it cleaves after certain amino acids. And when you do this then in silico, so computationally, then you also need to cleave those proteins up, and with specifying this enzyme, you tell the algorithm what to do. Then also we select variable modifications, which are important. Also we hear later why. For the computational analysis for identification, and then if you want to do label-free quantification, here you switch that on. And also you need to specify faster files, because we have a database search algorithm, we need a database. Then you also select fixed modification. Often there is nothing to do, but sometimes you have specific experiments where you also want to change that. And that's it. I think we could live with that. And so the next what you need to do is then to set the number of threads, because also here in MaxQuant we have multiprocessing to speed things up. And we would recommend to set the number of logical processor units of your laptop or of your servers. So if I have 8, I probably would select 7 if I want to still do other things like working with my Word or reading emails. And then we are ready to press start, and then it does everything for you. So also here, where does MaxQuant run? So initially, MaxQuant was developed for Windows, but already quite a while ago, we started to develop to support the Linux platform. And so here is also, if you want to know more, look into that publication. And then, so usually for Windows and for Linux, you have the MaxQuant cmd.exe, where you can start MaxQuant on the command line. And there you basically, for Windows, say MaxQuant cmd.exe, and then you give the MQ file where you specify all your parameters. And this is the same what you do then in Linux, with the only difference that you write mono before. And then it should run. And also when you want to run MaxQuant on Linux, there is you don't need to download a specific version to run for MaxQuant that runs on Linux, because we use the same code that runs on both platforms, and so that exactly, so you download it and run it, and only writing for Linux mono. Then we are also working to support soon, hopefully, Apple and Mac. So in theory, it should already work also on the command line, but we haven't fully tested it. But feel free to try it out. And if you have any problems, let us know, and then that can also help to speed things up. So in terms of letting us know, here I want to mention important links here. So first of all, where you can download MaxQuant is www.maxquant.org, and also for Perseus we have a download page where you can do that. Then also, if you are new and if you or even if you are advanced, there, of course, it's sometimes depending on what you do, there are always questions, and we have a Google group where you can look up. And also, as I started, I had also a question, how I do that, and then someone recommended me the Google group, and I looked up, and then I saw quite a very good discussion on that, which answered my question. So if you don't know anything, go there, look it up. Maybe you find already the answer you would need, and if not, just start a new thread. There's a good community that discusses topics. And then also, if there is any problem, we also offer UTrack to report bugs. And here I would highly encourage you also to write as many details as possible that helps us to fix the bug. Like, for instance, which version did you use, or which parameter settings did you use, which file did you analyze, was it a raw file? And also, like, we have an output file, a log file, and there it also writes then the error message. So if there is something, please add all the information to that. That helps us to better find the error, and then of course it helps you that the problem is faster solved. So also what we hear later, there will be a plugin session. So on GitHub there will be the source code where you can, if you develop your own plugins, you can upload it and then also download some. And also the last year, as Jürgen has shown, we had already many summer schools. So every year we record them and then we upload them to YouTube. So maybe, of course, after a long day you might have been already tired and you have just heard half of it. So here you can then go and just watch it again. Yeah. Also in terms of quantification, I want to give you a brief overview. So we have a label-free approach that does the quantification, that is MaxLFQ. And then there are all different MS1 labelling supported and also MS2 labelings. For MS1 labeling, the one that is missing is 15N. That is why the implementation is a bit more complicated, because usually for the MS1 quantification you don't need the identification first to do the quantification, but in that case we need to identify first, and this is not the typical flow in MaxQuant, that's why it takes a bit. Yeah, and what I also want to highlight here is that for label-free and MS1 labeling, you don't see any really a difference on labels, but here for the MS2, you see those report the IN that indicates the different channels where the quantification is then based on. Okay, that was the introduction. Now we are ready for the workflows, hopefully. So I will go through them and let's see how far I get, and then Jürgen will continue. So I also give you a brief overview of each steps. So first we start with the feature detection. So what is a feature? So here we look at the 3D peak information of the MS1 level, and then we also want to assemble this to isotopic pattern. And then we do the initial search, and with the initial search the purpose is that we collect recalibration points to do the mass recalibration. And what does the mass recalibration is that it does get rid of the systematic errors. So after we have then corrected for the systematic errors, we have then high mass accuracy, where we can start then the main search, where we try to identify all the MS2 spectra. And of course, also the score does not always tell everything if that is a true identification or not. So we also calculate a false discovery rate. And there usually, by default, a threshold of 1% is applied, which is the default value. Then if we have reliable identifications, we can also do second peptide search. And this is, in some cases, you have co-fragmentations, and then you also would like to identify those in the MS2 spectra. Then we also do retention time alignment. And this is because we want to do then later on match between runs. And this is for the quantification, like if we have two raw files where the data is quite similar, it can be that in one run we have an identification which is missing in the other one. And there we can look up in the other one at the expected position to see if we have an additional MS1 feature there. And if it's there, we can also use it for quantification. After that, we do then the protein group assembly. And then we also apply the false discovery rate on that. And then we do label-free quantification. And after we are done with that, we write out the output tables. So output tables, again, there are many different ones, and we will have a separate lecture on that, lecture 9 specifically for the output tables, where you hear where to find which information. And then for the label-free quantification, we also have a separate talk, and after this lecture, we will hear more about the Andromeda database search. So now let's go into those workflows. Also, what I wanted to mention here is those are not all workflow steps that are implemented in MaxQuant, so only the main important ones that we can focus on them. So here we can see, like, based on the MS1 level, a peptide, but when we have the mass of a peptide, we would think, okay, there is only just one peak for a mass. But this is not the case. Here we have, for one peptide, 5 peaks. And why do we have them? This is because we have natural occurring isotopes. And so here, in case of carbon, we see, okay, the most abundant one is the C12, but we also have C13, so which is roughly the difference of 1 Dalton. And then also we have a heavy nitrogen and a heavy oxygen. And then those heavy carbons or nitrogens, they are causing then mass shifts, and this results then in an isotopic pattern. So we have 5 peaks for one peptide, and here we would like to identify those and assemble those. So also, if we are able to see those isotopic patterns, this is depending on the mass resolution of the mass spec. And so, for instance, if you have low resolution on the top here, then you see, okay, you would see a mixed distribution, but the resolution is not high enough to really see that this is an isotopic pattern. And so, but if you have high resolution, you can really look then into this and can see this isotopic pattern. And if you have ultra-high resolution, you can also see when you have the monoisotopic peak, which is the first one, you can see then that the next one is a heavy carbon, for instance. So for the rest of the summer school, we are not talking about the ultra-high resolution, but I just wanted to mention it to you, that it's out there, and that the community might already develop some tools that also includes or supports ultra-high resolution, that it's possible to analyze that on a large scale. So again, this is another view on the isotope pattern, and so now we will explain you how to assemble it. So here, the first hill here basically is a 3D picture, and then we first try to assemble all the 3D peaks, and then if we have all of them, we check, okay, can we assemble those to isotopic pattern? And here, when we have charge 1, we would expect that the difference between those peaks is 1 Dalton. And these are some indication which allows us to do that. There are more, I will explain you later. And yeah, does it work better? Yes, it does. Thank you. So so we try to identify those 3D peaks and then we assemble those. And so let's see now how it works to detect the 3D peak. So first of all, we do that based on the 2D information, and on that we need to do centroiding. This way of centroiding is done based on the overtrap data or any Fourier transformed data, because this is regular and smooth. But for TOF data, for instance, this is not that easy, but usually the vendor provides already the centroiding information. So let's see how it's done here for overtrap data, for instance. So when you have here this 2D peak, you would start with the local maximum here, and then basically you look at the left and at the right, and then you see does it go to 0, or you basically find a local minimum, the next one. So either here at 0, and then you define your boundaries, or it can also be that here is a shoulder, and then you would set here the cutoff before it starts going up again. And then you fit the Gaussian on the top of the most intense 3 or 5 peaks, and that's how you position your centroid there. And as for the intensity, you sum up then all intensity of that curve, and this is then the intensity of your centroid. So we have all the centroid information, and then we do this for all of the 2D information, and then we would like to connect those centroids to a 3D peak. And how it's done is, so basically you check if there is another centroid with the same mass or within a tolerance of 7 ppm. And if that is the case, you connect those. So you basically slide around the retention time. And sometimes due to low quality, it can also happen that there is no centroid present in the next scan. And here you would not just stop. Here because of quality, it can be just missing, and that's why we skip that one where we don't see anything, and then we look one further and check if that centroid is again fulfilling our criteria. And so we keep doing that until there is no centroid within the correct mass range, and then we have assembled the 3D peak here, which looks has that shape. And here, this is another plot of the base area of the 3D peak. And what you can see here is that it's not just a rectangular, that the base area, but it really follows nicely the shape of the 3D peak. And also what you can see here, I hope you can see, is in the middle the centroids. And because we have tolerances, it's not just a straight line. And here it's quite zigzag, but in higher intensity region you have a nicer line, so that means also it's more accurate in high intensities. And what we do here now is that we want to get an estimate mass for the peptide, and then we calculate based on the weighted mean depending on the intensity, because it's better quality here. And also this is then a better estimate, so if we calculate it that way, then just having one centroid that represents the mass of the peptide. Then also here, like we can do this, what we just did with many peptides. And so we have the estimate, and then because of the zigzag, we know the mass error. And this we can then calculate, and then we get for every peptide error distribution. And this error distribution tells us then the tolerances for each individual peptide. And this allows us then later on, because we can see there is a peptide, but it's really badly measured, and we have to apply later on for the database search wider tolerances to find possible peptides, and some are really nicely measured in a good quality, and there we can apply very strict tolerances. And this is super nice because for other search engine you need to just define a wide tolerance to also cover the low quality peptides, and here you have individual ones. Then we have assembled, detected now the 3D peak, and as I said, we do this with every peak to try to assemble it, and then we try to find the isotopic patterns of these peaks. So this, we have 3 main criteria, and they have to be fulfilled in order to get an isotopic pattern. And so the first criteria is that we look at the mass difference. So here, if we assume like it's charge 1, then the difference between the monoisotopic peak, which is the first one, and the second one should be about 1 Dalton apart. And if that is the case, we look at the second criteria. And of a peptide, the average elemental composition is roughly the same, even though the sequences are different. And this allows us to model a distribution. And here we apply the averaging model. So we, based on that, we calculate on the monoisotopic peak of the measured one model. And then this is quite accurate. And this allows us to compare, is this what we measure really similar to the model? And so here in the second criteria, we look at the intensities of this isotopic pattern. And so we calculate then a correlation, and then we apply a threshold. So it needs to be similar. And then we do this also again over the elution time. And there again, we calculate a correlation, and then if it's above a certain threshold, also this criteria is fulfilled. And yeah, then we have the isotopic pattern. So when we do MS1 labeling, we also would like to assign the light and the heavy pairs. And this is done in a similar way than we assembled the isotopic pattern. So again here we look at the mass differences between the monoisotopic peak of the light and at the heavy, and we check the difference. So for instance, if you have lyc in your peptide should have on the C-termini lysine, and then you know that this you can, based on that, you have the differences between the light and then the heavy. And if you have charge 1s, for instance, you know this is 8 Dalton apart. And then also it can, of course, happen that you have miscleavages, and then you suddenly have 2 lysines in your peptide, and then you also you have for charge 1 8 times 2, so 16 Dalton. You would expect the difference, and this helps you. This is the first criteria. And then we also look at the correlation of the isotopic patterns again, and also for the elution profile. So of course it can also be that you not only have light and heavy, but that you have light, medium and heavy. And to assemble those pairs, it's again the same procedure, but you first try to find the pairs between the light and the medium, and then the light and the heavy, and then you also connect the medium and the heavy. Okay, so now we have already done the first step to detect the features. And so here what we have done, we first found the 3D peak, then we assembled it to an isotopic pattern, and then we also try to find the labeling pairs, the light and the heavy, and so on. And now we are talking about the first time about the database search. So here the initial search, and this is again just for the purpose to collect recalibration points to do the mass recalibration. So here, to give you a quick outline, so for this we use the integrated database search engine Andromeda, and it's similar to MaxQuant, but additionally it can also identify second peptides. It has the individual peptide mass tolerances, and as I said, it's fully integrated into MaxQuant, and it also controls the false discovery by calculating posterior error probabilities based on the target decoy approach. Then it's working nicely on large search spaces, and you can also do unspecific search. So again, here you don't analyze all data in your raw file, you just take a portion out of it in order to get enough recalibration points. And also we don't calculate the FDR at this point. We take for this recalibration point identification about a score of 80. So here we collect many recalibration points, and this is also a big advantage, because the alternative would be that you do spike-ins, that you know where the correct mass should be. However, for large data sets, you would need to do many, and then even then it's sometimes they're not enough to be able to correct for the error. That's why it's really good here that we get of the data set really this internal mass recalibrance. And what you can see here is the error in ppm. And so here this is the error over the retention time shown, and here the error over the mass. And here you can see that the error is quite jumping around over a retention time of more than 120 minutes. And we would like to correct for this, because these are the systematic errors we want to get rid of. And so based on this jumping around, we can see that the error correction function can't be linear. So we have to fit a nonlinear curve through the data points here, and then we can subtract that points from all the data points in the raw file, not just for the ones that you've used in your first search. And this helps them to get rid of the systematic errors, which you can see here then. So this is done then after the correction. And here you can see that the error is then nicely distributed around 0, and it has also smaller tolerances. So also at the bottom here, you can see the histogram that the data, the error before recalibration, and then also after recalibration. So before that, you can see that the error is really spread, so from 0 up to 10 ppm. And after the recalibration, you can see that the error is nicely centered around 0 and has a tolerance of 1 ppm. What we also can see is that we use that we have many data points for isotopic peak and for isotopic pattern and for the Silac pairs, and all those data points which we have, that should help to increase the precision, and this also then helps to lead then to a higher mass accuracy. So here we can see another plot showing the mass accuracy, the increase. So again, here we can see that it's nicely centered around 0. We have 1 ppm of mass accuracy or mass errors, tolerances, and then also so this is based on the recalibrated samples, and when we plot again those histogram over the unrecalibrated samples, then we can see nicely the difference and the improvement of the recalibration. So before it stretched out to 10 ppm, and here we are within 1 ppm, and this is a factor of 5 in mass accuracy gain, roughly. Now we are ready to talk about the quantification. So here we would like to calculate the ratio between the light and the heavy. And often there is a common question, like when you have the MaxQuant output tables, that you see a ratio there, and then you would like to recalculate this yourself, and then you take the ratio, and then you take the heavy divided by the light, and then you could see that there is a different ratio to that what is reported in the output table. And the reason is that it's probably different calculated than what you do, because what is not done is that you just sum up all the intensities over the isotopic pattern, and then you divide the heavy by the light. In MaxQuant implemented, it's different, and I show you now how it's done. So first of all, you take the monoisotopic peak of the light and the heavy, and then again you disassemble it, that you have the centroids for each of those 3D peaks, and then you calculate the median of all these centroids. And the median is then the ratio. You take then as a ratio, and this is also more robust, because in case if you have co-fragmented peptides, then you would end up having different intensities, and the median helps that doesn't disturb. Yeah?
So, like if you have a large peptide and the C12 peak is close to the ground, would you then take that C13 peak for the quantification, or?
So the algorithm doesn't rely on that you find the monoisotope. So it's basically, even if you don't see the monoisotope, it will just, from a fit to the averaging model, will see where the monoisotope is, and then correlates whatever is there in the two isotope patterns.
Okay. So now we have requantify, and so sometimes it can happen that you are not able to assemble MS1 labels, so the heavy and the light, because one of them is low abundant and has not enough intensities to be detected, but still you would like to quantify those. And in that case, you can do requantify. So how does it work? So here this is a heat map of the MS1 features, where you can see an isotopic pattern. And then you also got an MS2 spectrum, which is could be identified of that peptide. And based on the identification, you can see, then the peptide sequence, and also that it has a heavy lysine. And based on this, you can then, it's a heavy peptide, and you would like to try to find the light version of the peptide, which hasn't been seen before, and you can then calculate where the light partner should be. And here, for instance, we know we would expect the peptide to be in these positions here, and then if you find there is signal in that positions, okay, this is my light partner, and we can connect those and then also do quantification. But I think one has to say that if you want to know the numbers of the ratio exactly, you should be careful with that option, because it does it underestimates the ratio, and then you get different ratio values. So here this method just tells you if you're interested in the outlier ratios, so very extreme ratios, you can do this. But if you really need the exact ratio values, then you probably should not use that. Then also you need to normalize for the peptide ratios. So what we can see here in this plot is that you have two subpopulations, and with lysine labeled peptides and arginine labeled peptides. So the light one are the lysine ones and the arginine, and you can see that especially in higher intensity ratios that you have different means and these two subpopulations, and you don't want that. And this can be because of the purity of the labeled amino acids, and you need to correct for those. And also it's better to correct it here because then later those values are used to calculate the protein ratios, and that's why we do normalizations to not take the error later on with us. And so we calculate the mean of all those subpopulations and then we correct for it. Then for the protein ratio, we take then the mean over all peptide ratio. And again, the mean we take because it's more robust. And also if we, median, sorry. I thought about median, but said mean, so thank you for the correction. But it also luckily is written here correctly. Then also, and this helps then to have already a reliable protein ratio when you have just 3 peptide ratios. So for the retention time alignment, here this I will only mention briefly because this will all be in detail explained in the label 3 quantification session. But as I mentioned also already at the beginning of the talk, sometimes you would like to look up the features between runs, and this requires that you find exactly the position where you can read up. You need very accurate, first of all, masses, which we have already corrected for, but also the retention time needs to be aligned between the runs. And so here we also have a nonlinear retention time alignment, and then this helps us to get the correct retention times which is important for the match between runs. And here, for instance, we have 2 runs with isotopic patterns, and we can see here in one run the peptide is not identified, but in the second run it is identified. And with these accurate masses and retention time, we can then look up in the other run to see if we have a signal there, which we can then use for the quantification. And also what one has to see here, the match say here is match between run you should apply between similar data. Yeah, I think we are done now with the first part of the MaxQuant basics. So the second part will be then tomorrow in the afternoon by Jürgen. Thank you for your attention.